Hello friends, today I start with the problems in solution chapters of a chemistry. So now, before starting with this chapter, we try to cover up all the formulas which is covered in this chapter. So now we first start with the formulas, that is important formula which is covered in this chapter. Now first formula you see, that is the whenever you study the type of solutions, okay, in that we express the concentration of a solution in different terms. So first term, that is mass percentage of a component, means your solution is made up of two components, solute and solvent. So in that case you have to measure the mass in terms of gram. Okay, so that's why your formula is what? Mass percentage of a component, that is weight by weight, is equal to mass of component in a solution divided by total mass of a solution into 100. Now we see the next formula in which your component is expressed in a volume term. So at that time you represent, that is volume percentage of a components, which is equal to volume of a component divided by volume of a solution into 100. Now one thing is, remember, your unit is very important in this case. So volume unit is what? ml, liter, dm3, cm3. So at that time also you must know the conversion factor, that is 1 liter is equal to 1 dm3, which is equal to 1000 ml or 1000 cm3. Your ml and cm3 both are the same terms. Now next we represent the formula, that is mole fraction of a component. Now for mole fraction of a component, you represent it as X, which is equal to number of mole of the component divided by total number of mole of all the component. Means when you take a solution, in that you have a solute and solvent. These are two components. Okay. And if you have to find out the mole fraction of a solute component, so now your formula become number of mole of a solute divided by total number mole of your solution. Next, we study the part per million formula. Means if you have to convert, this is nothing but your concentration expression. Means you express the concentration in these different terms. So now part per million is equal to what? Number of part of a component divided by total number of a part of all the component of the solution into 10 raised to 6. Now next concentration term, that is nothing but your molarity. Now what is the meaning of molarity? This is in your last year standard also. That is molarity is nothing but what? Your number of mole of a solute divided by volume of a solution in liters. Now in this case also, your mole of any component, if you have to find out, so formula is fixed, that is mole equals to weight of that particular component in a gram divided by its molar mass. Now we study the next formula, that is molality. Now molality is equal to number of mole of a solute divided by mass of a solvent in kilogram. That is the difference between molarity and molality. When you said it is molarity, so at that time you express your solution in a volume, and whenever you said molality, so at that time you express your solvent in mass, that is in kg. So molality is temperature independent quantity and molarity is temperature dependent quantity. Now next concentration term is normality. Now what is normality? So normality is equal to number of gram of a equivalent of your solute divided by volume of a solution in liter. So always remember your normality and molarity is temperature dependent quantity because your volume of a solution may be vary with as the temperature is increasing or decreasing. Now next term is our next concept is our relative lowering of a vapor pressure. Now see, in this case P01 minus P1 which is divided by P01 which is equal to X2. Now X2 is what? X2 is nothing but your mole fraction of a solute. Okay. Now next is your P01 and P1. P01 is what? Vapor pressure of your pure solvent. Okay. And P1 is what? Their partial vapor pressure. See, whenever you have P01, that is nothing but your vapor pressure of a pure solvent, and whenever it is P1, so at that time it is vapor pressure of your solution. Next is another colligative property, that is elevation in boiling point. So now in elevation in boiling point, your formula is delta T is equal to TB minus TB naught. Now in this case, what is TB and what is TB naught? So TB is what? Boiling point of your solution, and TB naught is what? Boiling point of your pure solvent. So whenever naught sign is there, means that is for a pure solvent, and TB is what? That is for a solution. Now this delta TB which is equal to, means when you study the elevation in boiling point, means that is the difference. So which is equal to Kb into 1000 into W2 upon M2 into W1. Now in this case, Kb is nothing but what? Oscilloscopic constant. Then 1000, that is the term which is required because it is in a gram. Then multiply W2 means that is weight of your solute, divided by M2 means what? That is weight, that is nothing but molar mass of your solute, and W1 is what? That is weight of your solvent in a gram. Whenever it is in a gram, so at that time it is nothing but you have to multiply with a 1000 term. Now next, that is another colligative property, that is nothing but depression in freezing point. Now depression in freezing point, for that delta T is equal to TF naught minus TF. So now in this case also TF naught is what? That is freezing point of your pure solvent, and TF is what? Freezing point of your solution. Okay. Now next delta TF is equal to Kf into 1000 into W2 upon M2 into W1. Similar to as your elevation in boiling point, here also depression in freezing point, you just introduce a new constant, that is gyroscopic constant, which we represented as Kf into 1000 into W2 upon M2 into W1. Both ebullioscopic, both your elevation in boiling point and depression in freezing point. Both the formula having same, that is multiply with 1000, multiply with W2 upon M2 into W1. But only difference is what? That is constant. It is in a depression in freezing point, it is represented by Kf, and elevation in boiling point, it is represented by Kb. Now, whenever you have 1000, you multiply with 1000, means what? They are represented in a kg. Now next, another colligative property, that is osmotic pressure. For osmotic pressure, your formula which is equal to CRT. CRT means what? You express concentration in mole. R means that is a gas constant. T means that is your temperature. Now, these terms only means your osmotic pressure. Now, in this case, your C is nothing but N by V. So, in place of N, we just write W2 upon M2. Okay. So, in place of C, what is you write? That is N divided by V. But your N is nothing but what? W2 upon M2. So when you rearrange this term, and if you have to find out the molar mass of your solute with this osmotic pressure as a colligative property, so you can rearrange the formula and you get M2 is equal to W2 into RT upon pi into V. Now we start with the next, that is our Van't Hoff factor. Now Van't Hoff factor means what? That is nothing but normal molar mass upon abnormal molar mass, or your Van't Hoff factor is nothing but is observed colligative property divided by calculated colligative property. Means as far as you studied that colligative property is nothing but relative lowering of vapor pressure, elevation in boiling point, depression in freezing point, and your osmotic pressure. So you can observe colligative property divided by calculated colligative property. So another term for Van't Hoff factor is nothing but total number of mole of particles after association or dissociation divided by total number of a mole of a particle before association or dissociation. Now we have to apply this colligative property as per our Van't Hoff factor. Means we have to apply the Van't Hoff factor to that property. Now P01 minus P1 upon P01, which is equal to I into N2 upon N1. Now as in our relative lowering vapor pressure, our formula is what? P01 minus P1 upon P01, which is equal to X2. Now X2 is nothing but what? Your number of mole fraction of your solute. So similarly, in this case, just what they do, they apply the Van't Hoff factor, means correction factor for this colligative property, means which is equal to I into N2 upon N1. Now next colligative property, that is elevation in boiling point. For that, what is our formula? Delta TB is equal to rest of the KB into 1000 into W2 upon M2 into W1. That is same. We just apply the correction factor. That is nothing but we multiply with Van't Hoff factor, that is I. Next colligative property is depression in freezing point. So now in this case also formula is same, but we have to multiply with I. Now for osmotic pressure also our formula is what? CRT, that is nothing but and C in place of C we write N2 by V. So before for correcting we just multiply with the I. So pi is equal to I into N2 RT upon V. Now next is we have according to Raoult's law for a solution of volatile liquid the partial vapor pressure of each component in a solution is directly proportional to its mole fraction. Means what? Your P is equal to P1 not extra or P2 which is equal to P2 not into x2. Now using Dalton's law of partial pressure of a total pressure of a solution, it's calculated as P total is equal to P01 plus P02 minus P01 into x2. So now we start with the problem number 1, that is based on your Henry's law. So now what is exactly Henry law? Henry law is stated that your solubility of a gas is directly proportional to your pressure. So that Henry's law, in that case your solubility will be represented by S. P is nothing but your pressure of a gas in a bar, and KH is nothing but your proportionality constant, which is called as a Henry's constant. So now we see the problem first, that is the solubility of N2 gas in a water at 25 degrees Celsius and 1 bar is 6.85 into 10 raised to minus 4 mole per liter. Now in this case you know that is bar is a unit of pressure. Similarly they gives you the solubility of your N2 gas in water, that is 6.85 into 10 raised to minus 4 mole per liter. So for this means for N2 gas dissolved in a water you have to find out the Henry's law constant, means you have to find out KH here. So now here according to your Henry's law your formula is what? S is equal to KHP. So we rearrange the formula. So now KH is equal to S upon P. So now we see that is 6.85 into 10 raised to minus 4 upon 1 bar. So our answer is 6.85 into 10 raised to minus 4 mole. See, dm cube and liter both are same term. So you can represent as mole per liter or you can write mole per dm cube per bar. So unit is also important. Then only you get a full marks. Now next is what? Now S is equal to KHP. Now see, you have to find out what? Molarity of N2, B part is what? Molarity of N2 gas dissolved in a water under atmospheric pressure when partial pressure of N2 in atmosphere is 0.75 bar. Means in this case you have to find out solubility of your N2 gas but under the pressure of 0.75 bar. So now in this case S is equal to, first of all you get the KH value, that is 6.85 into 10 raised to minus 4, that you have to apply into 0.75 bar. Now bar term is cancelled and your S is now become 5.138 into 10 raised to minus 4 mole per liter. Means first of all the question is what? They ask you first of all Henry's law constant. Means if once you get a KH value, then afterward what you have to find out? The molarity of N2 gas dissolved in a water. Means you have to find out the solubility of N2 gas in a water under pressure of 0.75 bar. Means in first case the solubility is given for 1 bar and in B part you have to find out the solubility under the pressure of 0.75 bar. So for that, we first of all find out the KH value and we put that KH value in B part question and we multiply KH with that pressure, so you get a answer. Now next sum is on your relative lowering of vapor pressure. The vapor pressure of a pure liquid A and B are 450 mm mercury and 700 mm mercury respectively and at temperature of 350 Kelvin. Now find the composition of a liquid and vapor if total pressure is 600 mm. Now in this case you have a two composition, that is A and B. Now see, composition A and B are in the solution, so they are represented as X1 and X2. Now your total pressure is what? Which is equal to P01, means the vapor pressure due to your pure liquid A plus P02, means that is the vapor pressure due to your composition B. Means when you write P01, P02, so that is the vapor pressure of your pure solvent or pure component, okay, which is into X2. Now see this, in this case P01 is given to you, that is 450 mm and P02 is 700 mm mercury. Now what is the total pressure? Means P that is equal to 600 mm mercury. Now we have to put all this value in the above equation. Now what we write? So 600 mm mercury, which is equal to 450 mm mercury plus 700 minus 450 into X2. Now see, in this sum, what we have to find out? The composition of a liquid, means you have to find out X2 as well as X1. So first we find out X2, then we find out X1. Okay. So now which is equal to, so 600 is equal to 450 plus 250 into X2. Okay. Now we have to rearrange the term. That 600 minus 450, which is equal to 250 into X2. Now 150 is equal to 250 into X2. So X2 is equal to 150 upon 250, which is equal to 0.6. So see, in this example, we have to find out the composition of both the liquid, that is A also and B also. So first of all, we find out the composition of X2, means that is nothing but of your composition B. And then as we know, that is X1 plus X2, which is equal to 1. So X1 is equal to what? 1 minus X2, means which is equal to 1 minus 0.6, which is equal to 0.4. So see, this is nothing but your sum based on your relative lowering of vapor pressure, means on your Raoult's law. So Raoult's law, as you know, that is total pressure is equal to the pressure due to your pure liquid of component A plus, then you have to, in your bracket, you have to subtract the vapor pressure of component B minus component A in a pure liquid form into X2, and X2 is nothing but your mole fraction of your pure component B or your solute. See, 2 is representation for solute and 1 is for solvent. So this sum is based on your Raoult's law concept. Now we see the next problem. But before that, see, in this case also composition of A and B in vapors are Y1 and Y2. So as per Raoult's law, what is your formula? So P1 is equal to Y1 into P and P2 is equal to Y2 into P. So P1 is equal to P01 into X1 and P2 is equal to P2 naught into X2. So now in this case Y1 is equal to P1 upon P, which is equal to, so now P1 is what? P01 into X1 upon P. So P01 that you know. What is the vapor pressure of your pure liquid of composition A? So that is 450. X1, the value you got, that is 0.4 divided by total vapor pressure, that is 600. So 450 into 0.4 upon 600, which is equal to 0.3. So similarly, if you know Y1, you can find out the Y2 also. So Y2 is equal to 1 minus Y1. So 1 minus 0.3, that is nothing but 0.7. So one thing is, remember, in this case, what you do, you have to find out the composition of A and B. For that, first of all, you find out the X2 term. Okay, X1 and X2 means what? That is the mole fraction of your composition in a solution. Okay, and that also you know by this formula, means P1 is equal to X1 into P01. That is, you know, that is P1 is equal to X1 into P1. So in this case, you have to find out the composition. For that, we write as Y1 is equal to P1 upon P, which is equal to P1 is what? P01 into X1 upon P. So which is equal to 450 into 0.4 upon 600, which is equal to 0.3. Okay. So always remember, according to Raoult's law, when you have to find, this is very important, that is P1 is equal to P01 into X1, P2 is equal to P02 into X2, but your P1, for find out composition of P1, how you find out? P1 is equal to Y1 into P, so Y1 is equal to P1 upon P. Okay, so next sum is based on the relative lowering pressure. Means in this sum, we have to find out the molar mass of your solute. See, for relative lowering of vapor pressure, what is our formula? That first of all you must know. First we read the sum and then what is given, that we have to write. See, what is sum? A solution is prepared by dissolving 394 gram of non-volatile solute. See, this is non-volatile solute. Means that is nothing but your W2, because weight is given in a gram. So W2 is equal to what? 394 gram. In how much of water? That is 622 gram. Means that is nothing but your W1. So W1 is equal to 622 gram. Okay. Next is what? The vapor pressure of a solution is found to be 30.74 mm mercury at 30 degrees Celsius. See, in this case they given you the vapor pressure of a solution. Means they given you P1 term. Okay. And next what they write? If the vapor pressure of a water at 30 degrees Celsius is 31.5 8 mm of mercury. Now see, this is the vapor pressure of a water. Means water is a pure solvent. So you write it as symbol as P01, which is equal to 31.8 mm of a mercury. Okay. What is the molar mass of a solute? Simple question is there. Means what is the here M2 here. Okay. Means M2 is what? That is the molar mass of your solute. So for this, which formula we taken? That is P01 minus P1 upon P01, which is equal to delta P upon P01. Now, which is equal to W2 into M1 upon M2 into W1. Now, you know the values that is given in your equation, that is given in your problem. What is W2? What is W1? What is M1? What is P1? What is P01? Okay. So now you have to put this value in this equation. So 31.8 minus 30.74 divided by 31.8, which is equal to 394 into 18 upon M2 into 622 gram. Now M2 term you have to brought on one side and you have to rearrange all this term on one side. So one thing is, remember, at the time of your writing the values in a formula, you have to write with a unit also. Then only what is the unit of your component that you have to find out, that unit must be in a right way. Okay. So M2 is equal to 11.4 upon 0.033. So your answer is 342 gram per mole. Now we start with the next problem. Problem is based on your elevation in boiling point. Now see, what is the problem? 3.795 gram of sulfur is dissolved in a 100 gram of a carbon disulfide. Now in this case, sulfur is what? Your solute, and carbon disulfide is your solvent. Okay. This solution boil at 319.81 Kelvin. Means when you dissolve sulfur in carbon disulfide, so you get one solution, and that solution is boiled at 319.81 Kelvin. So what is the molecular formula of sulfur in a solution? And if the boiling point of your pure solvent is 319.45 Kelvin. Now see, as we studied, that is we studied delta TB. So elevation in boiling point, that is represented by delta TB. Okay. Now delta TB is what? So it is nothing but TB naught minus TB. Means it is nothing but TB minus TB naught. So now in this case, delta TB formula that you know, which is equal to 1000 into Kb into W2 upon W1 into M2. Now in this case, you have to find a molecular formula. But before finding molecular formula, you must know what is the molar mass of your sulfur in this carbon disulfide solution. So in this case, which quantity is given to you? 100 gram of carbon disulfide. That is nothing but weight of solvent is given to you. So W1 is equal to 100 gram. Now W2 is what? It is equal to 3.795 gram. Okay. Now they given you two boiling point. One boiling point is due to the solution and another boiling point that is due to your solvent. Now one thing is always remember, elevation in boiling point means what? Your pure solvent have a boiling point lower than that here and you add solute in that. Means if you take water, so what is the boiling point of water? 100 degrees Celsius. But if you add some solute in that, so its boiling point is increases. Means your elevation boiling point, that is delta TB is equal to what? Boiling point of your solution minus boiling point of your solvent. But both this quantity in Kelvin only. Okay. So in this case, delta TB is what? 319.81 minus 319.45. So which is equal to 0.36 Kelvin. Now, as we know, that is W1 is given to you, W2 is given to you, delta TB is given to you. Now you have to find out the M2. So now what we do, which is equal to 1000. Now gram per kg into, now see, 2.42 Kelvin kg per mole, that is the ebullioscopic constant which is given to you, into 3.795 gram upon 0.36 Kelvin into 100. Now if you see this, see in this case your weight of solute and solvent is given in gram. So that's why first of all only we multiply with 1000, then only your answer of M2 is coming in gram per mole. Okay, so in this case your answer is 255.10 gram per mole. So now what you have to find out? The number of atom in a molecule of sulfur. So how will you find out that? So see, in this case atomic mass S, which is equal to 32U, okay, and your number of atom in a molecule of sulfur, which is equal to molar mass of a sulfur divided by atomic mass of a sulfur. Now from this formula you find out the molar mass of sulfur, that is 255.1 divided by atomic mass of sulfur is what? 32. So 255.1 divided by 32, your answer is nothing but 7.92, which is nearly equal to 8. So now in this case means your sulfur dissolve in carbon disulfide. So at that time the molecular formula for sulfur is S8. Okay. Now next is the sum is based on depression in freezing point. Okay. So now see what is the sum. 1.02 gram of a urea when dissolved in 98.5 gram of a certain solvent. Okay. In this case they just taken any solvent. Okay. So what happened? See, this is a based on depression in freezing point. Means your pure solvent have a more freezing point and your solution have a less freezing point. Okay. So what happened after adding urea in certain solvent? Your freezing point of that solution is decreases by 0.211 Kelvin. Okay. Means delta TF they given to you. Now 1.609 gram of unknown compound when dissolved in 86 gram of a same solvent. Means when you add urea in certain solvent, their freezing point is decreases by 0.211 Kelvin. And when you add any unknown solute in a same solvent, so at that time its freezing point is decreases by 0.34 Kelvin. So calculate molar mass of the unknown compound. Now see, in this case you have a two different solute, but you dissolve in a same solvent. Now what you have to find out? The unknown solute molar mass. Okay, so what we do? See, first of all, we try to find out Kf for urea in a certain solvent. Okay, as soon as we get the Kf value from urea in that particular solvent, we can find out the molar mass of that unknown compound in that solvent only. Okay, now see, for urea, what is your W2? 1.02 gram. Okay, now W1 means weight of solvent is 98.5 gram. Now delta TF is what? 0.211 Kelvin. And M2, that is molar mass, is 60 gram per mole. Okay, for unknown compound, W2 dash means for unknown compound they taken as W2 dash, that is 1.609 gram. W1 dash, that is 86 gram. Delta TF dash, which is equal to 0.34 Kelvin, but you have to find out the molar mass of that unknown compound. Now formula is same, that is delta TF is equal to 1000 into Kf into W2. So that formula is same, means delta TF is equal to 1000 into Kf into W2 upon M2 into W1. Okay, for this is for what? Urea. When you add urea as a solvent in that solvent, and when you add unknown compound, unknown solute in that solvent, so your formula is rearranging to 1000 Kf, that is same, which is equal to, in place of M2 you write M2 dash into delta TF dash into W1 dash upon W2. Now we have to put the values in that. So now see, for urea, what you write? 1000 into Kf, which is equal to M2 is 60 gram per mole, delta TF for urea is 0.211 into 98.5 gram upon 1.02. Okay, so now you got one answer, that is 1247.01 gram Kelvin per mole upon 1.02. Now 1000 kf is same for both of the solvent, means solvent is same, only solute is different, so Kf is same. So now we apply for the unknown solute, that is 1000 Kf is equal to M2 dash into delta Tf dash into W1 dash upon W2 dash. Now in this case M2 doesn't know you, means you have to find out M2 dash. So M2 dash into 0.34 into 86 upon 1.609. So in this case, your first equation will be for urea and second equation, that is for unknown solute. Now you have to compare your first equation with second equation because your solvent is same. So now you are rearranging, that is 1247.01 gram Kelvin per mole upon 1.02 gram, which is equal to M2 dash into 29.24 Kelvin upon 1.609 gram. Okay, so in this case we rearranging the term and we get M2 dash, which is equal to 1247.01 gram Kelvin per mole into 1.609 gram upon 1.02 into 29.24 Kelvin. So your answer becomes 67.3 gram per mole. Means in this case, for find out the molar mass of unknown solute, we have to compare two different solute but in a same solvent. Okay, their depression in freezing point, both the term are different, but you have to compare because their chiroscopic constant will be same, and that term you have to cancel out, and you have to just compare one urea solute with another unknown solute. Okay, now we move to the next sum, that is for related with your osmotic pressure, that is next colligative property. So now sum is what is the molar mass of a solute if solution is prepared by dissolving 0.822 gram of it in 300 mdm cube. Now in this case mdm cube is nothing but what? Ml also, because mdm cube is nothing, dm cube is nothing but liter. So ml means in this case it is nothing but 300 ml of water has an osmotic pressure of 149 mm mercury at 298 Kelvin. So don't confuse with mdm cube means what? That is nothing but ml only. So now as you know what is osmotic pressure, so pi is equal to CRT. Okay, so in place of C you can write N by V. So N is nothing but what? W2 upon M2. So you have to rearrange that term. And now what is your formula? M2 is equal to W2RT upon pi V. Now which are the quantity that is given in your problem? So now see, W2. W2 is given to you, that is 0.822 gram. Okay. Now R. See, in this case, if you see, that is R which is equal to 0.08205 dm cube atmosphere per Kelvin per mole, and temperature is 298 Kelvin. Pi is what? 149 mm mercury. But see, your R is given in atmospheric pressure. So that's why your pi is also need to be converted into atmospheric pressure. Okay. So now 1 atmosphere is equal to 760 mm mercury. So 149 mm mercury means how many atmosphere? So 149 mm upon 760, which is equal to 0.196 atmosphere. Now once again see your R unit. The volume unit is given in dm cube. Okay, means they given you liter. But if you see in your problem, they given you 300 mdm cube. Matlab it is given in ml. So you have to convert it into dm cube by dividing with 1000. So V is equal to 300 ml, which is equal to 0.3 dm cube. Now as we know that is W2 is known, R, T, pi is known to you, V is known to you. So you can find out M2 from this. So M2 is what? 0.822 into 0.08205 liter atmosphere per Kelvin per mole into 298 upon 0.196 into 0.3 dm cube. So which is equal to, your answer comes, that is 342 gram per mole. See, in this case your weight is given in gram. So that's why your molar mass is also coming in a gram only. That is nothing but gram per mole. Okay. Now we start with another concept, that is our Van't Hoff factor, and on that basis we study the next problem, that is 0.2 molar aqueous solution of KCl freezes at minus 0.680 degrees Celsius. Okay, calculate Van't Hoff factor and osmotic pressure of a solution at 0 degrees Celsius. Okay, and Kf, that is your chiroscopic constant, is given to you, that is nothing but 1.86 Kelvin kg per mole. Now see, in this case your solution is freezes at minus 0.680 degrees Celsius and your pure solvent is freezes at 0 degrees Celsius. Okay, so when you do that is 0 minus of 0.680 degrees Celsius, that is nothing but your 0.680, and see your delta TF is always in a Kelvin term. So in this case also, if you convert 0 into Kelvin, so that is 273, and you do that is for 0.680 means 273 minus 0.680. So your 273 cancel, and your answer in minus, that is in a 0.680 Kelvin. Now delta TF is equal to what? Kf into m. Okay, that is nothing but your molality of your solution. So now delta TF, okay, which is equal to Kf is given to you 1.86 kg per mole into 0.2 mole per kg, which is equal to 0.372 Kelvin. Okay. Now see, in this case 0.372 Kelvin it is. Now how you calculate I from that? See, in this case you have to find out the Van't-Hoff factor. So Van't-Hoff factor is what? Which is equal to delta TF upon delta TF0. See, delta TF0 is what? That is, you observe, means 1.86 Kelvin kg per mole into 0.2 mole per kg. So in this case, what happened exactly? See, your I is what? What is the I? So Van't-Hoff factor, when you calculate, so at that time, what you write? That is colligative property, that is theoretically obtained, divided by colligative property observed. Okay, means in this case delta TF, that is you observe, that is delta TF is equal to what? 0.680, means that is the observed reading. Okay, but what is calculated reading? That is you take from that, that is 0.372. So in this case I is equal to delta TF upon delta TF naught. Okay, so I is equal to 0.680, which is a theoretical, means that is given to you, that is 0 degree Celsius is given to you, freezes, means that is the observed term, sorry, 0.680, 0 degree Celsius. So that is the observed term, but calculated term is what? 0.372. So 0.680 upon 0.372, your answer is 1.83. So Van't-Hoff factor is 1.83 here. So now what you have to find out? The osmotic pressure of a solution, means you have to find out osmotic pressure at 0 degree Celsius. So how you find out? Pi 0 is equal to MRT. MRT means what? N2RT upon V. So in this case, which is equal to 0.2 into 0.08205 into 273 upon 1 liter. So your answer become 4.48 atmosphere. So now your I, which is equal to 1.83, which is we calculate earlier. So which is equal to pi upon pi 0. So pi is equal to 1.83 into calculated value, that is 4.48. So your answer become pi is equal to 8.2 atmosphere. Now we see the next problem, which is based on degree of dissociation. Okay, in this formula, in this problem, what is the problem? That is 0.01 molar aqueous formic acid solution freezes at minus 0.021 degree Celsius. Calculate its degree of dissociation. So Kf is equal to 1.86 Kelvin kg per mole. Now delta TF is what? In this case aqueous formic acid solution. That you know water is freezes at 0 degree Celsius. So delta TF is what? 0 degree minus 0.021 degree Celsius, which is equal to 0.021 degree Celsius, or you have to write 0.021 Kelvin also. That is one and the same. Now delta TF. Okay. Now in this case delta TF is equal to I into Kf into M. So M is given to you, that is 0.01 molal. So delta TF 0.021, which is equal to I into 1.86 into 0.01 mole per kg. Okay, so your I become 1.13. Now degree of dissociation formula is what? I minus 1, alpha is equal to I minus 1 upon N minus 1. Okay, now in this case I minus 1, which is equal to I is known to you, that is 1.13, and N is 2. Okay, so alpha is equal to 1.13 minus 1, which is equal to 0.13, means that is nothing but your 13%. Okay, now we see the next sum. See which of the following solution will have maximum boiling point elevation and which have a minimum freezing point depression, assuming the complete dissociation. Okay, now see, such type of question may be asked in your MCQ also. So they gives you, that is a 0.1 molar KCl. In second option they give you 0.05 molar NaCl. In third they gives you 1 molar AlPO4, and in fourth they give you 0.1 molar MgSO4. Now see, boiling point elevation, freezing point depression, all are colligative property. Okay, that depend upon the number of a particle in solution. The solution having more number of particle will have a large boiling point elevation, and that having less particle will showing the minimum freezing point depression. Okay, now we see KCl. So KCl is breakdown into K plus and Cl minus. Now see, in this case KCl is taken, we take, that is 0.1 molar, and K plus and Cl minus ion is formed. So all are in 0.1 molar. So now total particle in solution, that is nothing but 0.2 molar. Okay, now we see NaCl. In NaCl is also dissociated as Na plus Cl minus. So now NaCl we taken as 0.05 molar. So Na and Cl dissociate, you use 0.05 and 0.05. Means total particle in solution, that is nothing but 0.1 molar. Now next AlPO4. AlPO4 gives you Al3 plus PO4 3 minus, that is 1 molar. So 1 molar, 1 molar, 1 molar. So that is the total particle in solution, that is nothing but 2 molar. Okay. Now MgSO4. MgSO4 gives you Mg2 plus PO4 2 minus. So MgSO4 we taken as 0.1 molar. So which given as 0.1 molar Mg2 plus and 0.1 molar PO4 2 minus. So total particle in a solution will be 0.2 molar. So in this case, if you see, AlPO4 solution contain highest mole, and hence it have a highest number of particle, and then it have a maximum of elevation in boiling point. Similarly, NaCl solution have a minimum moles per particle, and it has a minimum depression in freezing point. Okay. Now the next sum is, assuming complete dissociation, calculate molality of an aqueous solution of KBr whose freezing point is minus 2.95 degrees Celsius. Kf for a water is 1.86 Kelvin kg per mole. See, this is base, that is KBr is given as K plus and Br minus. So now I is given to you, that is mole of particle after dissociation divided by mole of particle dissolved. So in this case, How many mole of particle dissociate? So 1 and 2. So 2 divided by kbr, that is 1. So which is equal to 2. So now delta TF is equal to I into Kf into m. So delta TF is what? 0 minus of 2.95, which is equal to 2.95 Kelvin only. Because see, 0 degree you have to convert, you have to add 273. Similarly, for minus 2.95 degrees Celsius also you have to convert it in Kelvin. You have to subtract from 273. So 273 term are cancelled and your answer is coming in 2.95 Kelvin only. So M become delta TF upon I into Kf. So delta TF is 2.95 Kelvin upon 2.186 Kelvin kg per mole, which is equal to 0.793 mole per kilogram. So in this way, we complete the problem in a solution, and thank you for listening.